Today I'm going to show you how to work with the series and be able to determine if a series converges absolutely, conditionally, or if it diverges. So let's take a look at the conditions first, define these terms, and then we'll take a look at some examples. Suppose we're looking at a particular series, and the big question is, we want to know if the series converge or diverge. So first thing we're going to think about, well, what happens if you take the absolute value of the terms? If you take the absolute value of it, will it converge? Say it converges. If that happens, then the original series converges, which means that then the original series, we can conclude it converges absolutely. So when you put the absolute value, it converges, the original series converges, therefore we can say it is an absolute convergent. The second scenario you can run into is the following. If you take the absolute value of your series, it diverges. But the series on its own, the original series, converges. So in absolute value, it diverges, but on its own, it converges. We say then that the series converges conditionally. So it's not an absolute convergent, but it's a conditional convergent. And the last thing we're going to say is, what if they both diverge? When you take the absolute value of your series and the series on its own diverges, then it's divergent. There is really nothing else to say about that series other than it doesn't matter what you do to it, it's going to diverge. So let me show you an example on each cases so that way you're familiar with how to determine when it's absolute convergent, conditionally convergent, or divergent. All right, so here's our first problem. Our question is to ask ourselves, will this series converge absolutely, conditionally, or is it divergent? So if you look at this example I have here, it has this -1 to the n plus 1 power. Well, this is the alternating series. So let's go ahead and do the alternating series test. If you're not familiar with what any of these tests are that we're going to do, I'll leave a link in the description box for you to check out every test that we can run for a particular series. Since this is an alternating series, we'll go with the alternating series test first, see if it converges, and then we'll throw in the absolute value. So, well, let's check this out. So this is your formula for AN or UN. In alternating series test, I mentioned it's a UN. Really depends on what textbook you're using. Doesn't really matter. So, first condition you want to satisfy for the alternating series test is that your terms, UNs, are positive. And you can see by observation that if this is our UN, without the alternation, the terms are positive when you plug in values for n, 1, 2, 3, any large values. It's always going to be positive. So the first condition is observed. The second condition of the alternating series test is to determine that your term UN plus 1 is less than or equal to UN. So your one future term is less than the previous term. So that you can do it two different ways. You can do the comparison in the inequality, or you can test the first derivative function, see that it's negative, then certain interval. So if I plug in n plus 1 into my formula, I will have 1 plus n plus 1 over n plus 1 squared. Is that less than or equal to UN? That's going to be the original formula. Well, let's check this out. If you simplify the numerator, this is 2 plus n over n plus 1 squared, less than or equal to 1 plus n over n squared. So you see that this is definitely true because here I have more terms on the denominator. Here I only have n squared. Overall, my denominator is very large on the left side, so the fraction value will be very small. So that's also checked. Now, the last thing I'm going to show is that the limit as n approaches infinity of the UN, it's going to be 0. Well, let's check. So that's the last condition we need to show for the series to converge by the alternating series test. So we take the limit as n approaches infinity of 1 plus n over n squared. And this limit is for sure 0. All right, so what does that say? Well, this series converges on its own. So this is a convergent by the alternating series test. Now let's throw in an absolute value and see if it converges. If it does, then we will say it is absolutely convergent. So I'm going to go ahead and take my series and look at the absolute value of it. So we're looking at the series from n equals 1 to infinity of -1 to the power n plus 1 times 1 plus n over n squared. So that's our an or un, right? So I copied it correctly. When you throw in the absolute value in your sequence, the terms of your series, this will disappear because -1, when you take the absolute value, it's going to disappear. So we're really looking at this series, n from 1 to infinity of the absolute value, 1 plus n over n squared. Now, this is always positive, and that's what we said in the alternating series test, that these guys are always positive without the alternation. So I can throw out the absolute value and just look at that series. So, well, now that we are looking at this series, we can start thinking which test can we apply to see if this will converge or diverge. I'm going to go with comparison. So it looks like I can just create another sequence by looking at their leading term from the numerator and the denominator. So I can say that, well, let's take a look at this series. So this is going to be the series I'm going to create with the leading terms from the numerator and denominator, n over n squared. Now, which way will the inequality go? Well, the inequality will go this way. So this is definitely greater than what I came up with, n over n squared. Now, if you simplify n over n squared, that simplifies to 1 over n. So this is the sum from 1 to infinity of 1 over n. Now, what do we know about this series? This is a harmonic series. So this is a famous harmonic series, and we know this diverges. So this is a harmonic series, which is divergent. So this one lies below the one we're looking at. So therefore, if whatever lies below, if it diverges, then whatever lies above will also diverge. So that will make this series diverge. So therefore, we can say that when you take the absolute value of this original series, it's actually divergent. But on its own, the series we're looking at was convergent. So because it diverges in absolute value, so diverges when we do this, when we take the absolute value of our series un. So therefore, we can say that this series, the sum from n equals 1 to infinity of -1 to the power n plus 1 times 1 plus n over n squared is a conditionally convergent. So that's the conclusion we can draw for this series. All right, so here's our second example. We want to know if this is a absolute convergent, conditionally convergent, or divergent. So we see factorials and power, so let's throw in the absolute value and test for absolute convergent. Because if it's absolute convergent, then there's no need to test for conditional convergent. It's definitely a convergent. So let's go ahead and do that. So we're going to take a look at the series in absolute value. So we're looking at n equals 1 to infinity of absolute value of 100, -100 to the n power over n factorial. So this is going to help us to drop the negative sign. So we can just look at the series 100 to the n power over n factorial. So this is easy to work with. So we know this is our an. Now, to find the convergence or divergence of this series, we're going to apply the ratio test. So let's use the ratio test. So for this particular series, we're going to use the ratio test. So for ratio test, we're going to determine the an and an plus 1 term. Well, we know this is your an term. So an plus 1 term would simply be plugging in n plus 1 where there is n in the formula. So it'd be 100 to the power n plus 1 over n plus 1 factorial. So that's your an plus 1 term. Let's use the ratio test. So we take the limit as n approaches infinity of absolute value of an plus 1 over a sub n. So this would be the limit as n approaches infinity of a sub n plus 1. Well, that's this term right here. And we divide by a sub n, which is this guy right here. And now feel free to drop the absolute value because all of these terms are positive. So we can drop the absolute value really. So we have 100 to the power n plus 1 over n plus 1 factorial over a sub n. That's 100 to the n over n factorial. And then we change the fraction in the following ways. We simplify algebraically. That's the same thing as writing 100 to the n times 100. So I'm separating these pieces right here using the laws of exponent. And on the denominator, n plus 1 factorial, you can write it as n plus 1 times n factorial. And then I reciprocate the bottom fraction. So this would be n factorial over 100 to the n. So I did some algebra and some simplification as well. Now I can cancel out like terms. So this one and this one, they can cancel. 100 to the n and 100 to the n, they can also cancel. So what we're left with is the limit as n approaches infinity of 100 over n plus 1. Now, if you take this limit, you're going to get 0 because the denominator is growing, the numerator is a constant. Now, the ratio test tells us if you take this limit and if you get a value less than 1, then it is an absolute convergent. So we get a value 0, which is less than 1. So we say that this series that we're looking at from 1 to infinity of negative 100 to the n power over n factorial. So let's just go back. Yep, that's the one we're looking at. By ratio test, this is an absolute convergence. So by ratio test, it converges absolutely. And we know if it converges absolutely, it's definitely conditionally convergent, so no need to test for that. So for this problem, let's go ahead and see if this is absolute convergent. So we're going to throw in an absolute value in our series. So we're going to look at the following to see if it is absolutely convergent. So we're going to take a look at the series from 1 to infinity, absolute value of negative 1 to the n times n over n plus 1. So that will throw away the negative term. So we're simply looking at the series from n equals 1 to infinity and in absolute value of n over n plus 1. Now here you can also throw away the absolute value because these terms are positive. So let's just take a look at that. Now let's take a limit of this. So I'm going to apply the nth term divergence test here. So if you take the limit as n approaches infinity of your a sub n, so this is our a sub n, or u sub n if you want to write it that way. This is n over n plus 1. And this limit is 1. So because this limit is 1, it's not 0 by the nth term divergence test. This actually diverges. So it is not an absolute convergence. So this implies that our series diverges. So the absolute divergence test doesn't work. It's not absolute convergent. Now let's test for conditionally convergent. So we're going to take a look at this series and see if it is conditionally convergent. So we're looking to see if it is conditionally convergent. So we're looking at the series from 1 to infinity of negative 1 to the n times n over n plus 1. Now here again, if you can try to apply the alternating series test because there is alternation here, but an easier way to do this would be to actually, again, use the nth term divergence test because we already know what this limit is. If you take the limit of that, it's going to be 1, not 0. And because of the alternating factor in front, this right here, so it'll keep bounds between 1 and negative 1 and 1 and negative 1. So it'll be easier to show that if you do the nth term divergence test on this, take the limit as n goes to infinity of negative 1 to the n times n over n plus 1, this limit does not exist because the terms are keep on alternating and it doesn't let the limit settle at any value. So by that, also by the nth term divergence test, this is going to diverge as well. So therefore, we can say that this divergent, this is a divergent series. So here's our last example for today. So we want to know if this series converges absolutely, conditionally, or if it diverges. So always test for absolute convergent first. So I want to know if this is absolute convergent. So I'll throw in the absolute value and see what happens. So we have the sum from n equals 1 to infinity, absolute value of -1 to the n times 1 over square root of n. So this simplifies to the sum from 1 to infinity. So you'll throw out the -1 factor. So you have 1 over square root of n. Square root of n can also be written as n to the 1/2 power. So this is 1 over n to the 1/2. Now you should realize that this is a p series. So this is a p series because it has the form of a p series. Now your p happens to be 1/2, which is less than 1. So in that case, we know that this is a divergent p series. So this is divergent p series. So what that tells us is that this series is not absolute convergent. So this is not absolute convergent. Now let's go ahead and test to see if it converges conditionally. So now we're going to see if it converges conditionally convergent. So let's call it CC. So I'm going to take a look at this series on its own. So we have the sum from 1 to infinity of -1 to the n times 1 over square root of n. So if you try to apply the alternating series test here, it looks like it will probably converge, but let's check. So the first condition we need to satisfy is that our formula for UNs is positive, and they are. So if you just look at your formula right here, because that's your U sub n, it is going to be 1 over square root of, so let's write it down. This is 1 over square root of n. So if you plug in n equals 1, 2, 3, they're all positive terms. So this is checked. The second condition is that they're decreasing. So un plus 1 is less than or equal to u sub n. Well, that also seems to be true. So this is 1 over a square root of n plus 1. Is that less than or equal to 1 over square root of n? Yeah, we can agree on that. That's true. Because we have more terms here in the denominator, here you have less terms, so overall the fraction value is going to be less on the left side. So that also holds. Now let's take the limit. So if you take the limit as n approaches infinity of your un, what do we have? We have the limit as n approaches infinity of 1 over square root of n. And clearly we can see that this limit is 0. So this is also checked. So it's actually convergent on its own. So this is convergent by the alternating series test. So now we can say that, well, it doesn't converge when you throw in the absolute value, it converges on its own. So therefore, it's actually convergent conditionally. So we can say that this series right here, this is a conditionally convergent. So that's what we can conclude about this series, because by throwing an absolute value, we got a divergent series. But if you just look at it on its own, it converges. All right, so I'm going to stop right here. I hope this helped you understand conditionally convergent, absolute convergent, and divergent as well. All right, so take care, everyone. I will see you guys next time.